Now we're in Chapter 6, Diesel Engine Power. We can define the terms used to describe power generation in commercial diesel engines, how engines produce torque and power, construct a formula required to calculate power equations, calculate brake power using actual engine data, interpret a simple fuel map, and convert brake horsepower to kilowatts. Calculate indicated power using the Planck formula. Objectives. We need to determine how the brake-specific fuel consumption and explain how it's used in diesel engine fuel map. OEM torque and power graphs and check their mathematical accuracy. Explain how load is determined and how load data is used. Define the term B-life and explain its relation to engine longevity. Explain how the term torque rise and why it's advantageous to operating a vehicle on a highway. Relate engine brake power to the actual power requirements of a highway rig and its load. 1,600 years ago, Hero and Watt, they're in Chapter 5, many heat engines have been designed and built, but none achieved better than 1% thermal efficiency. That means the power that was created, the actual work, was very little and the heat was great. It's important that diesel technicians acquire a basic understanding of power production. How we measure power. It's to simplify some of the concepts of power, and OEMs, original equipment manufacturers, will most often publish power analysis specifications using only the standard systems. The definitions and formulas. It's necessary to understand language used to describe it. And we're introducing a series of definitions that will work towards developing them into the power formula required to calculate power. The first law of thermodynamics. Power, energy can neither be created nor destroyed. However, the way it manifests itself can be changed. The energy released by combusting fuel in an engine cylinder that cannot be converted into kinetic energy is described as heat or rejected heat. So you're making a ratio of work or kinetic energy, and you're creating heat, and a portion of the event is actually rejected heat. Effects of heat energy. It's easily converted into mechanical energy, then this can happen in many ways. The term heat energy is used to describe a wide range of engines that convert the heat potential of fuels into mechanical energy. Force. It's generally defined in terms of effects it produces. We can also call it work. It should be remembered that force can be exerted with no results. How force is produced in an engine. Work is accomplished when the application of force produces a result. Torque is the turning effort, and power is the rate of its doing work. Horsepower. The horsepower formula, the importance of time, and power calculations to achieve the understanding. Brake horsepower. Power is measured at the flywheel, and it's usually less than calculated power, and we're going to take a look at that and find out why. That brake horsepower is torque times RPM, how much time it's working, divided by 5252. Brake power, or kilowatts, is torque times RPM divided by 9429. Here we're going to look at three different Mack MP10 engines. We have a Mack MP10 at 605 horsepower, that's the green line. We have a same basic engine configured at 515 horsepower, that's the red line. And we have the blue MP10, which is configured at 565 horsepower. So you're going from 515 to 565 to 605 horsepower. And what we're seeing here is that the torque rise occurs quickly, and it's occurring between 1100 and 13 to 1400 RPMs on all three engines. The red line, which is the 515 horsepower, is falling off first, and followed next by the blue line, which is at the bottom of the on the torque graph. And you see that the green line, the MP10 605 horsepower, produces more torque and it falls off a little bit later. But all three of them are producing their maximum torque in the range of 1500 RPMs at the torque rise, and you see that it falls off quickly, and horsepower will continue to rise over time. The conversions, these are conversion charts that you can go to foot-pounds, Newton meters, horsepower, kilowatts, horsepower into British thermal units, BTUs, and a metric horsepower, which is a kilogram meters per minute. Let's take a look at a simple fuel map showing torque rise and brake-specific fuel consumption. What we have here is peak turbo efficiency with a constant geometry turbo. So it is not a variable geometry turbo like we have in more modern trucks. But you see that the idle speed up to approximately RPM, the brake-specific fuel consumption actually drops off, and it rises again as it approaches rated power. And this is more theoretical, but you need to understand that the fuel consumption is going to change as the torque rise occurs. The indicated power formulas, these are more scientific than actually indicated for technicians just to understand that there are scientific ways to utilize mean effective pressure, the length of the stroke, and the cross-sectional area of the piston, and the number of power strokes per minute, and the number of engine cylinders. And it's somewhat theoretical as compared to this Caterpillar C15 performance chart. And you can see actual torque in foot-pounds and power and brake horsepower in these applications. The SAE, Society of Automotive Engineers, a brake power rating is known as the most reliable because they have specific test criteria and conditions that are rigorously detailed in order to determine the power rating, the brake horsepower. Potential energy is stored potential. It's often misused, and we commonly use the term potential energy otherwise. Mechanical efficiency, here we have a situation where we're going to be looking at the energy it takes to turn the engine to come up with the actual brake horsepower, but actually how much power is delivered to the wheels on the truck. Continuous brake horsepower, it's running the engine at a specific speed, producing a determined amount of horsepower, so that we're not compromising engine longevity, and we're giving the engine the best chance to have a long life. Dynamometer is the most practical way to test power output of diesel engine and trucks. This tests the power produced at the wheels, meaning the engine power must be transmitted through the drivetrain and wheel assemblies, and we do expect a 15 to 25% drop between brake horsepower at the flywheel to what is actually delivered at the wheels. Torque rise originated from the days of earlier hydromechanically managed engines. They had rigid fuel maps and constant geometry turbos. The torque rise occurs between peak torque RPM and rated speed RPM. Torque rise profile comes from the graphic representation of the upper portion of the fuel map, as shown often in engine OEMs on their sales literature. However, torque rise profile is perhaps best understood as being the desired operating range for the engine. For a truck with a mechanical transmission, this is important because it defines the upper and lower RPM shifting limits. Fuel map performance. Generally, a fleet truck engineered for line haul highway application requires fuel map programming or governing in older engines for fuel economy. Therefore, to the disappointment of the driver, lacks a high torque rise characteristic. Specific fuel consumption is fuel consumed per unit of work produced. This datum decreased as brake-specific fuel consumption, BSFC, is often diagrammed into power fuel map performance graphs to demonstrate fuel efficiency through the torque rise of an engine. Load is usually defined as the ratio of power developed to the normal rated power at specific RPM of an engine and is expressed as a percentage. Detroit Diesel, DD15, 15-liter performance curves. And here we see the modern engine has a variable geometry turbo. It has a sophisticated Bosch amplified common rail fuel system. And you can see that the torque rise is achieved between 1,000 and 14 to 1,500 RPMs. When you go faster with the RPM, your actual brake horsepower will be achieved at, the 455 is achieved at about 1,800 RPM, but the torque begins to drop off at 1,500 RPMs. Here's a Navstar 13-liter max force engine. It achieves a pretty quick torque rise, peaking out between about 1,100 to 1,350 RPMs and drops off quickly at 1,450 to 1,500 RPMs, but the horsepower rises and flattens out approximately at the 1,400 to 1,800 RPM. B-life and power. The projection in percentages of engines that will fail at various mileage intervals. Truck OEMs are very concerned with the cost of operation and what is a good B-life for an engine. If an engine has a B10 rating of 550,000 miles, according to the OEM, 10% of the samples are failing at that mileage. If the same engine has a B50 rating of 725,000 miles, then 50% of the sample engines have failed by the time they've run 725,000 miles. Engine configuration, engine speed, and torsional forces. The number of cylinders in any engine will define the geometric interval, expressed in crank degrees, between firing pulses. These torsional forces, sometimes called torsionals, are amplified at slower engine RPM levels when the time interval between power stroke is greatest and can affect the driven components of the drivetrain. Run slow, gear fast. Today's diesel engines, which are designed for fuel economy, combined with low emissions, tend to wind out at much lower RPM levels than those a generation ago. This type of engine program is referred to as run slow, gear fast governing. How much power do you need? Speccing out a truck engine is a specialty. There are many variables to consider that they're difficult to outline in a way that is readily understood. It takes about 255 brake horsepower to move a truck down a level asphalt road at 60 miles per hour with no wind. As soon as we add 1% uphill grade, we need another 65 brake horsepower, and so now the engine requires 320 brake horsepower. Parasitic loss, such as air conditioning and engine fans, typical viscous fans, can take up to 15 brake horsepower running at only 2% at a time. They all have to be factored into the brake horsepower requirement for a specific truck. Summary. Engine exists in many forms: kinetic, potential, electrical, and chemical. Energy is the capacity for performing work. Force is defined in terms of its effects it would produce, despite the fact that the application of force does not necessarily result in work being accomplished. Torque is defined as turning effort, that is, the twisting force, such as may not necessarily result in work accomplished. Work is accomplished when force produces a result. Movement produces work. The power is rated of producing work, as such, is always related to time. Brake horsepower is power measured at the flywheel of the engine. Indicated power is calculated power using engine specifications and does not factor in friction and pumping losses, therefore it's less reliable, indicated power. When an engine torque and engine RPM are known, brake horsepower can be calculated. Indicated power can be calculated if mean effective pressure, MEP, stroke, bore, and power strokes per minute and number of engine cylinders are known. Mechanical efficiency is brake power specification divided by indicated power specification expressed as a percentage. Brake power is measured at the flywheel is typically 10 to 25% more than the brake power measured at the drive wheels of the truck. It takes a certain amount of power to go from the flywheel, through the clutch, through the transmission, through the drive shafts, differential, and axles out to the wheel end. So this is where we're going to see a 10 to 25% reduction of power from brake horsepower to actual power delivered to the wheels. Torque rise is desirable in highway diesel engines. It occurs as the engine is pulled down by the load from its rated power RPM to its peak torque RPM. Load is the ratio of power delivered to the rated power at the same RPM as expressed as percentage. Running an engine in the lower RPM portion of the torque rise profile, especially high torque rise engines, creates torsional oscillations that can affect the engine drivetrain.